The following program is brought to you by Caltech.
Good evening. My name is Tom Sofer. I'm the chairman of the Division of Physics, Math, and Astronomy here at Caltech. Before I introduce our speaker, I need to announce that the next lecture in the Watson Lecture Series will be on April 24th and will be by John Grotzinger, the Fletcher Jones Professor of Geology. He will speak on the Mars Science Laboratory, the search for habitable environments. The best part of my job is to be able to introduce speakers in this series from the Physics, Math, and Astronomy Division. And so tonight it's really my great pleasure to introduce our speaker, John Preskill, the Richard P. Feynman Professor of Theoretical Physics. The title of his chair really is a clear statement of the esteem with which he is held by his Caltech colleagues. John is a Princeton and Harvard graduate and has been a member of the Caltech faculty since 1983. When he came to Caltech, John's research focused on elementary particles, cosmology, and gravitation. In the mid-1990s, he changed course and focused his research on quantum computation and quantum information theory. He developed quantum error correction, which invigorated this field, propelling it into the forefront of physics research. John is the co-director of Caltech's Institute for Quantum Information and Matter, which is supported by the National Science Foundation and the Gordon and Betty Moore Foundation. In addition to being a world-leading researcher, John is an outstanding teacher, having twice won ASCA Teaching Awards and having mentored more than 40 PhD students in his career. John is also a great communicator of the excitement of science through his contributions to the blog Quantum Frontiers, which is on the IQIM website. For those of you who are interested, and I highly recommend that you look at the website and his blog. It's iqim.caltech.edu. A lesser publicized talent of John's, although it's certainly equal to his others, is as a poet. He's the poet laureate of the PMA division. When he introduces speakers, he usually does it with a poem that demonstrates his erudite training. I can't match his poetic skills, but I'll quote from a poem that one of his students at a recent celebration of a milestone birthday for him used. I think it was his 39th birthday or something like that. So part of the poem is, an expert on particles, fields, and forces, he juggled axions, symmetries, and courses. But somewhere along the proverbial way, quantum computers became his dossier. John does a much better job. I'm not sure whether John's talk tonight is going to be in iambic pentameter, free verse, or haiku. But I know that this will be an exciting lecture as John tells us about quantum entanglement and quantum computing. If you have questions after his talk, please come up to the podium and he'll take the questions here. With that, let me introduce John Preskill.
Well, thank you very much, Tom. My talk tonight is really about science, but it's also in part about technology. Quantum technology. I'm using this laptop, and it seems pretty cool, but we all recognize that the technology that might impress us today is going to be surpassed in the future by new technology, which we can't really expect to imagine today. But it can be fun and instructive, just the same, to speculate about future technologies. And I'll admit I'm not the ideal person to engage in that kind of speculation. I'm not an engineer, I'm a theoretical physicist. And I can't really claim to be particularly knowledgeable about how computers work. But as a physicist, I know that the crowning achievement of the past century has been the development of quantum theory, and it's natural to wonder how the emergence of quantum theory in the 20th century is going to impact 21st century technology. Quantum theory is now over 100 years old, but still there are deep ways in which quantum and classical systems differ that we're really just beginning to understand. A lot of those differences have to do with the physical nature of information. Information is something that we can encode and store in the state of a physical system, like the pages of a book. But we know that fundamentally, all information, all physical systems are really quantum systems. And so information is something that we can encode and store in a quantum state. And information carried by quantum systems has some famously counterintuitive properties. And that's why physicists like to talk about the weirdness of quantum theory. And we relish that weirdness and take great pleasure in it. But we're also asking more and more seriously whether it will be possible to put the weirdness to work to exploit the unusual properties of quantum information to perform tasks that just wouldn't be possible if this were a less weird classical world. And that desire to put weirdness to work has driven the emergence of a new field of science, what we call quantum information science, which from my perspective as a theoretical physicist derives much of its intellectual vitality from three central ideas: quantum entanglement, quantum computing, and quantum error correction. And it's my goal tonight to explain these ideas to you. So since we're going to talk about information, let's recall that any amount of classical information can be expressed in terms of indivisible units, bits of information. And we might envision a bit as an object, like, let's say, a ball, which can be either one of two colors, like red or green. And because we value our bits, we store them sometimes. I can put a bit inside a box, and then later on I can open the box, and the color ball that I put in will come out again, so the bit can be recovered and read. Well, by quantum information, I mean information carried by a quantum system. And for quantum information as well, it can always be expressed in terms of indivisible units, what we could call a quantum bit, or for short, a qubit. And for many purposes, we can envision a qubit as, again, an object stored inside a box, but where now it's possible to open the box in two complementary ways, through two doors, which I've labeled door 1 and door 2. So I can put a colored ball inside a box through either door number 1 or door number 2, and then later on, I can open that same door again, and the color ball I put in comes out again, so I can recover a bit just as though it were classical. But on the other hand, I could put information in a qubit through door number 1, and then later on open door number 2, measure it in the complementary way, and then what comes out is completely random and unpredictable, has probability 50% of being red, 50% of being green. So if we're going to read information in a quantum system, we have to go about it the right way. If we read it the wrong way, we'll actually destroy the information. And one consequence of that we can appreciate if we think about what it would mean to copy quantum information. Suppose I have a quantum copy machine. That would mean if I happen to have put information in a qubit through door number 1, I could copy that box, and then later on, if I were to open door number 1 for the original and the duplicate, the color ball that I put in would come out of both of those boxes. And similarly, if I happen to have stored information through door number 2, then if I made a duplicate, and later on I opened door number 2 for the original and the duplicate, the color I put in would come out of both boxes. That would be a quantum copier, but strangely, no such device is physically allowed to exist. We can't copy unknown quantum states. And the reason is that the copier, in order to copy the color of the ball that's inside the box, has to probe inside the box. It has to open the box in some way. And it might guess correctly the door I use, and then it would be able to copy the information without any problem. But it might make a wrong guess, opening the wrong door, and then it would damage the information, and it would not be possible after that to make a high-fidelity copy. So although we claim to be able to clone a sheep, we can't clone a qubit. Now, I'm describing qubits in this abstract way on purpose because it's useful to use that level of abstraction for the purpose of thinking about qubits. But any qubit in the physical world will have some physical realization, and I'll mention several of those in the course of the talk. But at this point, just so you'll have something concrete to think about, we can imagine a qubit encoded in a single photon or particle of light, and that single photon has an electric field. We could imagine that that electric field is oriented either horizontally or vertically, corresponding to the two colored boxes, two colored balls when I look into the box through door number 1. But on the other hand, I could consider the electric field oriented along these 45-degree rotated axes, and measuring the electric field in that way corresponds to opening door number 2 for the qubit. Now, if we really want to appreciate the important ways in which quantum information is different from classical information, then we're going to have to consider systems of more than one qubit. So let's suppose we have 2 qubits, and they could be far apart from one another. One's here at Caltech. The other is in the custody of my friend in the Andromeda galaxy. Now, some time ago, when both of these qubits were on Earth, they were prepared in a special state with some unusual properties. Namely, I can open my box through either door number 1 or door number 2, and when I do so, what I find is a random value, 50% probability of being red, 50% probability of being green. And the same thing is true for my friend in Andromeda. So that means that neither one of us, by opening his box, gains any information. All we do is generate a random bit. And that's kind of peculiar because with 2 boxes, we should have been able to store 2 bits of information. Where is that information hidden? The answer in this case is that all the information is actually encoded in the correlations between what happens when you open a box in Pasadena and you open a box in Andromeda. Because it turns out for this special state that we've prepared, if my friend and I both open door number 1, I might see a green ball or a red ball, but whatever I see, my friend is guaranteed to see as well. And if we both open door number 2, again, what I find could be red or green, but if my friend opens the same door, he'll see the same color that I do. Now, there are really 4 perfectly distinguishable ways in which a box in Pasadena could be correlated with a box in Andromeda, because we could see either the same color or different colors when we open door number 1 or door number 2. And we've chosen one of those 4 possible ways. That's 2 bits of information stored in the 2 boxes. But what's unusual in this case is that information is completely inaccessible locally. It's entirely stored in the correlations between these 2 distantly separated boxes. And that property of quantum information, that it can be stored non-locally and be locally inaccessible, that's what we call quantum entanglement. And it's the really essential way in which quantum information is different from classical information. Now look, correlations themselves are not such an unusual thing. We encounter them all the time in our daily lives. Usually my socks are the same color. And that means that if you look at one of my feet, then you already know for sure, before you look, what color sock you'll expect to see on my other foot. And it's kind of similar with these quantum boxes. If I want to know what my friend is going to see when he opens door number 1 in Andromeda, what I can do is open door number 1 in Pasadena and I can find out. And if, on the other hand, I want to know what my friend will find when he opens door number 2 in Andromeda, I open door number 2 in Pasadena and I find out what he'll see. So you might think the boxes are just like the sockses and there's nothing new here. But you'd be wrong. The boxes are not like the sockses. Why? The essential difference is there's just one way to look at my sock. But there are these 2 complementary ways of looking at a qubit. And that means that the correlations of qubits are richer and a lot more interesting than correlations among classical systems like socks. Now, this idea of quantum entanglement was first explicitly described in a paper by Einstein and two collaborators in 1935. Einstein found quantum entanglement disturbing. To him, it seemed so unsettling as to indicate that something was missing from our current understanding of the quantum description of nature. And that paper elicited some interesting responses, including one that was particularly perceptive by Schrödinger, who wrote a few months later, characterizing the situation, that the best possible knowledge of a whole does not necessarily include the best possible knowledge of its parts. So what Schrödinger meant was that even if we have the most complete description of this pair of qubits that nature will allow, I'm still completely helpless to predict what will happen when I open either door number 1 or door number 2 on my qubit. And it was Schrödinger who suggested using the word entanglement for this particular quantum type of correlation. And Schrödinger added, "It is rather discomforting that the theory should allow a system to be steered or piloted into one or the other type of state at the experimenter's mercy in spite of his having no access to it." And what Schrödinger meant was that it's really up to me to decide here in Pasadena whether I will open door number 1 and therefore be able to predict what my friend will see when he opens door number 1, or to open door number 2 and then be able to predict what he'll see when he opens door number 2, even though these boxes are far apart from one another. Now, Schrödinger understood that these correlations, though peculiar, do not allow us to send a message from Pasadena to Andromeda. No matter what I do, my friend, when he opens either door number 1 or 2, just sees a random bit, and he doesn't learn anything about what I've done, and therefore receives no message from me. Now, the theory of quantum entanglement did not advance very much for nearly 30 years, until the mid-60s. And then, starting with John Bell, we began to think about entanglement in a rather different way. Entanglement is not just something mysterious and peculiar. It can be a resource, something that we can use to do things that wouldn't otherwise be possible. I won't explain the details of what Bell said, but I'll try to give you the spirit of it. He said we can imagine two players, Alice and Bob, who are playing a cooperative game. That means both players are on the same side. They're both trying to win. And this game has the following structure. Alice and Bob each receive inputs, and they are then, based on their inputs, to produce outputs that are correlated in a certain way that depends on the inputs they receive. But under the rules of the game, Alice and Bob can't communicate in the middle of the game, so Alice has to produce her output before knowing what Bob's input was, and Bob has to produce his output without knowing what Alice's input was. Now, it may be that they have correlated bits which were distributed before the game began, which they can use, but for a particular game, it turns out that if they play the best possible strategy, they can win with, at best, a success probability of 75% if we average uniformly over the inputs they could have received. But we can consider a quantum version of the game in which, before the game began, correlated qubits were distributed to Alice and Bob, entangled qubits. And now it's possible for them to play a better strategy, an entangled strategy, or quantum strategy, which will enable them to win the game with a higher probability of success, over 85% instead of 75%. And so, the entanglement is useful for something. It allows you to win the game with a higher probability. Experimental physicists have played the game, and they've won, with the higher probability, above 75%, that Bell pointed out, is possible in a quantum world, but not in a classical world. So these quantum correlations really do seem to be part of the way nature behaves. Now, Einstein had derided quantum entanglement. He called it spooky action at a distance, and that sounds even more derisive when you say it in German. But you know, something we all love about science is that it doesn't matter what anyone's opinion is, even Einstein's. Nature is the way she's revealed to be in experiments. And if the experiments tell us that these super strong correlations are part of nature's design, then so be it. We have to learn to accept it and love nature as she is. So, Boxes are not like soxes. With boxes, we can win a game with a higher probability of success, 85% instead of 75%. Is that really such a big deal? Yes, yes, this is a big deal. And to appreciate why it's a big deal, we really should consider systems with more parts than just 2 parts. One way of thinking about it is we can imagine a book, which has 100 pages. Now, if this were an ordinary classical book, there would be print on every page. It's 100 pages long. I can read 10 of the pages, say, and now I know 10% of the content of the book. But suppose it's a quantum book. Each page is a quantum system, and the pages are highly entangled with one another. Well, then if I look at the pages one at a time, I just find random gibberish with no information content. There is information encoded in the book, but I can't perceive that information by looking at the pages one at a time. That's because the information isn't recorded in the individual pages. Hardly any of the information is recorded that way. It's almost entirely recorded in the correlations among the pages. And to read those correlations, we have to make a collective measurement on many of the pages at once. Well, we can think about it this way. Let's compare many classical bits with many qubits. Well, suppose it's 10 classical bits. I've got a lot of boxes, and there's a colored ball in each box. Well, there are 2 to the 10, 1,024 ways in which we could put the balls in those boxes, a lot of ways. But for any one of them, I can describe it to you very succinctly. I just tell you for each one of the 10 balls whether it's red or green. Suppose, on the other hand, I have 10 qubits. Well, now things are different, because it's not correct to say that each ball is red or green. Rather, it has some probability of being red or green. And there are complex correlations between what I see if I open door number 1 or door number 2 on one box as opposed to door number 1 or door number 2 on another box. So with just one typical highly entangled state of 10 qubits, if I wanted to completely describe those correlations, I'd have to write down a lot of numbers, about 1,000 numbers, for just 10 qubits. And as the number of qubits increases, if I have 20 qubits, well, now I need about 1,000,000 numbers to describe all the ways the qubits are correlated in some highly entangled state, or 1,000,000,000 numbers for 30 qubits. And when the number of qubits is still rather modest, just a few hundred or so, if I had some typical highly entangled state of 300 qubits, and I wanted to write down a complete description using classical bits of all the ways those qubits are correlated with one another, I would need to write down more numbers than the number of atoms in the visible universe. Clearly, it'll never be possible to write such a description down in terms of bits. And that property of quantum information, that we can't hope to express it in any succinct way in terms of ordinary classical information, was very intriguing to the Caltech physicist, Richard Feynman. And it led him to make the suggestion in the early 1980s that perhaps if we build a computer, a quantum computer that processes qubits instead of bits, then we'd be able to perform tasks that just wouldn't be possible with ordinary digital computers. Feynman's idea was that if we can't even write down in terms of classical bits the state of a few hundred qubits, then if we process the qubits, shouldn't we be able to do something that can't ever be emulated by an ordinary digital computer? Well, in the early 80s, when Feynman was thinking about these things, there was a Caltech undergraduate studying mathematics. And Peter Shor, like all Caltech undergraduates, as a sophomore learned quantum physics. And he never took a more advanced physics class than that. Also, like most Caltech undergraduates, Peter Shor remembered his quantum physics and called upon it some years later to make a rather amazing discovery. An example of a problem which seems to be hard for today's digital computers is finding the prime factors of a large composite integer. What Shor discovered is that if we can build a quantum computer, then the factoring problem would actually be an easy problem. It wouldn't be much harder to find prime factors than it is to multiply numbers together and find their product. Well, when I heard about this discovery in 1994, I was awestruck. I understood what it meant. that the boundary between hard and easy problems, problems that we can expect to solve someday with sufficiently advanced technology, and problems we can never hope to solve, that boundary is different than it otherwise would be because this is a quantum world, not a classical world. So, for example, about the hardest factoring problem that's been solved is finding the prime factors of a 193-digit number. And it took several months for a network of hundreds of workstations to solve that problem, collaborating over the internet. And from what we know about how those algorithms scale using that hardware, we can estimate that if we wanted to factor a 500-digit number instead, it would take longer than the age of the universe. So we don't expect to be able to factor 500,000-digit numbers with digital technology in the foreseeable future. But suppose, we have to suppose, because it's not true yet, that we have a quantum computer which has the same clock speed as that classical computing system. It can perform the same number of elementary operations per second as the classical computer. Then it would be able to factor the 193-digit number in 1/10 of a second and the 500-digit number in 2 seconds. There's a vastly different scaling of the resources we need to solve the problem as the problem size increases if we use a quantum computer. The important thing, well, you might say, does anybody care about factoring large numbers? Yeah, actually some people do. Because the public key crypto systems that are in widespread use to protect the privacy of financial transactions that we do over the internet, that crypto system is based on the difficulty of factoring and the difficulty of solving related number theoretic problems that quantum computers will be able to easily solve. So, perhaps some decades from now, when quantum computers are readily available, we will not be able to use the same methods we use today to protect our privacy. Alternatives exist, but it's not yet clear exactly what will be the best path for protecting information in the post-quantum future. But the really important thing that we learned from Shor is that if we look at the class of computational problems, there's an important distinction between the problems which are easy for classical computers and the problems that are easy for quantum computers. And the factoring problem seems to be one which is hard classically and easy quantumly. And it's important as a research theme to address the question, what else lies in that intermediate regime that quantum computers can do and classical computers cannot? It's kind of frustrating, though, because although a lot of theoretical work is being done on quantum algorithms, we can't run those algorithms, not yet, because we don't have quantum computers. So I chided my friend Eddie Farhi, who works on developing quantum algorithms, when I said, "We're very sorry, Eddie Farhi. Your algorithm's quantum. Can't run it on those mean machines until we actually got them." Well, the poem goes on, but you kind of get the point. So you can see that we'd really like to build quantum computers, and it'll be very exciting when we do. So what's the big deal? How come we don't have them already? What's taking so long? Well, you see, it's really, really, really hard. But you might ask, could it be that this isn't just a technological problem? Could there be some issue which, as a matter of principle, will prevent us from ever operating large-scale quantum computers that can solve hard problems? And in particular, what you might worry about is the problem of errors. Quantum computers would be particularly susceptible to the damaging effects of noise. Physicists sometimes like to talk somewhat fancifully about a quantum superposition of the dead and live state of a cat. And we never actually see in our everyday lives that sort of superposition of macroscopically distinguishable states, and we understand why that's the case. It's because a real cat can't possibly be perfectly isolated from its surroundings. And the interactions with the environment, in effect, immediately measure the cat, projecting it onto a state which is completely dead or completely alive. This phenomenon, which we call decoherence, helps us to understand why it is that quantum phenomena although they occur at the scale of individual atoms or electrons, are not generally seen in macroscopic systems. It's because those systems can't be perfectly isolated from the environment. Now, a quantum computer won't be much like a cat, probably, except that, like a cat, we won't be able to perfectly isolate it from the environment, and that will lead to decoherence, which will cause a quantum computer to crash. So if we're going to operate one successfully, we have to somehow find a way to protect it from the damaging effects of decoherence and any other possible sources of error that could cause the quantum computer to fail. Well, as you know, errors can be a problem even in the classical world. We all have bits, which we cherish, and which we'd like to protect. Everywhere, it seems, though, there are dragons lurking who delight in tampering with our bits, changing their values. But we've learned some ways of protecting ourselves against the dragons in the case of classical information. Because if I have a bit that I want to be sure to protect, I can store backup copies of the bit. And the dragon might come along and flip the value of one of those bits. But as long as it hasn't had a chance to flip 2 of the 3 bits, we're okay. Because I can employ a busy beaver who frequently checks to see if the bits all have the same value, and if he finds that one of them has a different value, he flips it back. And so we recover the original undamaged encoded state. We've used the principle that by redundantly storing information, we can protect it against errors. And we'd like to use that same principle in the case of quantum information. But at first, it seems like there might be some difficulties. As already noted, we can't copy an unknown quantum state. So we can't make a backup copy of the state of a quantum computer in the middle of a computation. That just won't work. And furthermore, there are more things that can go wrong with quantum information than classical information. If it's a qubit, then it's possible a dragon will open door number 1 and flip the color of the ball and then close the box again. But instead, he could open door number 2, change the color of the ball, and close the box again. Well, the first type of error is just like a bit flip error that occurs in classical information. The second type is what we call a phase error, and it really has no classical analog. Now, these phase errors are especially problematic because there's another way of thinking about them. A phase error could be caused if the dragon opens door number 1 and instead of trying to flip the bit, just remembers the bit or makes a record of what he saw. And the result of keeping that record will be to change the value of the qubit when we open door number 2. And because it's typically easier to remember a bit than to flip a bit, these phase errors are particularly pervasive and problematic, and we have to prevent them. Really, to resist decoherence and make a quantum computer work, we have to prevent the environment from learning anything about the state of the quantum computer during the computation. Any record left behind will cause the quantum computer to fail. It should be then that if a quantum computation does work, and then after it's over, you ask the quantum computer what just happened, it should answer, I forget. No record should be left behind. The final result of the computation can be published and broadcast, but the state of the computer during the computation must remain a secret. Well, what we need to do then is to store information in a way that the environment can't access it. And the trick is to use entanglement, to store the information in a highly entangled state. I can't store a qubit in a state of 3 qubits like we could store a bit in a state of 3 bits and protect against one error, but it works if I use 5 physical qubits to store 1 logical qubit. That can be done in such a way that if the dragon comes along and makes any observation or performs any operation he pleases on one of the 5 qubits, the dragon will learn nothing about the encoded state. That's because the information is encoded in a highly entangled state. And one of those qubits is just like 1 page of our 100-page book. It has no information in it. All the information is in how that one is correlated with the others. So we can have the beaver come along and check those multi-qubit correlations to see if they've been damaged and reverse the damage without the beaver ever finding out what the encoded state is either, and the information can be recovered in its original form. That's what we call quantum error correction. So even in the quantum world, it's possible by redundantly encoding information to protect it against errors. Now, so far I haven't said anything about what the hardware in a quantum computer will look like. Actually, there are a lot of different approaches to building hardware which are being developed, and it's not clear yet which will turn out to be the best for scaling up quantum computers to many qubits and many operations. But it's timely to mention one approach, since it was developed by Dave Wineland, who shared this year's Nobel Prize in Physics with another great experimental physicist, Serge Haroche. Wineland is a pioneer of the ion trap quantum computer. He has developed the technology to trap charged atoms, ions, using electromagnetic fields. The ions can be stored in a trap for a long time. And we might think of each ion as being in either its lowest energy quantum state, its ground state, or some excited state, which is long-lived, metastable. And so we can think of each ion as a qubit, which can be either a red or green ball, using our earlier abstract description. And you might think, since these are individual atoms, it would be hard to see what the state of each atom is. But actually, that's not very hard. We can illuminate all of the ions with laser light, and if we choose the frequency of the light appropriately, the ions which are in the green state won't interact with the light and they'll stay dark. But the ones in the red state will absorb and re-emit the light, so they'll fluoresce, glow visibly, and we'll be able to read out a series of zeros and ones. Now, this is a photograph under a microscope of two ions in Wineland's trap about a micron apart, clearly visible when illuminated by a laser. Of course, we want to do more than just read out the qubits in a quantum computer. We need to process the information, and we need in particular to get the ions to interact with one another in a controlled way. So here's one way that could be done. I could pick out an ion in a trap, and I could address it with a pulsed laser. And if I choose the frequency and the duration of that pulse in the right way, then nothing will happen if that ion was initially in the red state, but if it's in the green state, it will undergo a transition to the red state. And simultaneously, a vibrational mode of all the ions in the trap will be excited. And then we can pick out another ion in the trap, address it with a pulse laser, and if we choose the frequency and duration of that pulse appropriately, nothing will happen if the ions are not vibrating, but if they are vibrating, that ion will make a transition from the red to the green state and the vibration will stop. So what have we done? We've picked out two ions in the trap. If the original one had been red, nothing would have happened. If the original one is green, both of them change color. So if initially the first ion was in a superposition of red and green, then we will have created a correlated or entangled state of the two ions. And many such operations performed in succession would allow us to build up complicated many-qubit entangled states. We would, in other words, be doing a quantum computation. And such computations have been done in Wineland's lab and by other experimental groups on a handful of ions and with a modest number of operations. And now we'd like to scale that up enormously to thousands of qubits or millions of qubits. Well, I've described an ion trap the way a theorist like me thinks about it. But if you actually go to Wineland's lab, you get a shock. Things are a little more complicated. It turns out to take a lot of effort and a lot of technical ingenuity to make a quantum computer work, even when it involves just a handful of ions and a small number of operations. So scaling this up to the size where we can solve hard problems seems very daunting. It's very, very difficult, and it's not going to happen overnight. Now, there are other technologies which may in the end turn out to be more promising. One approach is to use superconductivity. Superconductivity means a current flowing through a wire without any resistance, so the current can persist, in principle, indefinitely. And with a superconducting circuit, although this isn't really the best way to do it in practice, one way in which we could encode a qubit is to consider two states of the persistent current in a loop of wire with the current flowing either counterclockwise or clockwise. Now, what's remarkable about this type of qubit is it really is a quantum object, and yet the persistent current involves the coordinated motion of billions of electrons. Another approach is to use a single electron, which has a magnetic field. And that magnetic field can be oriented either up or down, corresponding to the two states of a qubit. And what's remarkable about that physical encoding is that it's just one electron, and yet it's possible to manipulate and read out its state to quite good accuracy. So these are two other technologies which are under development, and at this stage we can do operations on a few qubits, perhaps up to of order 100 quantum gates or operations. Scaling things up looks hard, but over time we'll see whether it can be done. Now, the next hero of our story I want to tell you about is Alexei Kitaev, a member of the Caltech faculty in mathematics, physics, and computer science. But when I first met Kitaev, he was visiting Caltech for the first time from the Landau Institute in Moscow. And he gave a seminar, and as I was taking these notes, I felt a thrill, one of the biggest thrills of my scientific life, because I realized that what Kitaev was talking about was a potentially transformative idea. It was a very exciting day. And what I heard about from Kitaev was the idea that we can use topology to make a quantum computer work. Now, topology is the word that mathematicians use when they want to describe the properties of objects which remain unchanged if we smoothly deform the object without tearing it. Topology is relevant to quantum computation because we would like the way a quantum computer processes its protected information to remain invariant if we deform the quantum computer by introducing some noise or error. Now, physicists have known for a long time, for decades, that there are physical interactions that have a topological character. For example, I can transport an electron around a tube of magnetic flux, and that will modify the quantum state of that electron, even though the electron never enters the tube, in a way that depends on the enclosed magnetic flux. And that modification of the electron state is unchanged if I deform the trajectory that the electron followed. All that really matters is a topological property, that the electron wrapped once around the flux tube. Now, we know more exotic types of such topological interactions that can potentially occur for particles in two-dimensional systems, which we call these particles non-abelian anyons. So it turns out if you have many non-abelian anyons, there's a very large number of possible quantum states for those particles, and all of those states locally look the same. They differ only in the collective properties of many anyons. And that's just the type of encoding of physical information that we would like to hide the physical state from the environment, so a quantum computation can work. And not only that, we can process this information in a simple way, simple in principle, by exchanging the particles, which changes the many-particle quantum state of many anyons. So we can envision operating what Kitaev called a topological quantum computer. We would initialize it by preparing pairs of anyons, and then perform a sequence of exchanges of the particles so that the world lines of the anyons would trace out a braid in space-time. And to read out the computer, we would bring the anyons together in pairs and observe whether they annihilate one another and disappear or not. Well, what's beautiful about this idea is that the information that's being processed is very non-locally encoded and therefore protected from the damage that could be caused by decoherence. In principle, as long as the braid traced out by the world lines of the particles is the right braid, we'll do the right computation and get the right result. Well, at least that's how it's supposed to work. Now, the plight of the Enneon has been noted by the poets, who have said, "You and your buddy were made in a pair, then wandered around, braiding here, braiding there. You'll fuse back together when braiding is through. We'll bid you adieu as you vanish from view." Alexei exhibits a knack for persuading that someday we'll crunch quantum data by braiding, with quantum states hidden where no one can see, protected from damage through topology. Enneon, Enneon, where do you roam? Braid for a while before you go home. And this poem goes on too, but you get the idea. So this is the theorist version of computing with enneons. Can we really make it work in a real physical system? Well, here too, there's an interesting story that involves 3 members of the Caltech faculty, Alexei, Gil Raphael, and Jason Alicea. Alexei again started the ball rolling with a very stunning idea some time ago. He pointed out that it's possible under the right circumstances for an electron in a wire to split into 2 parts, for an electron in effect to be sawed in half. Well, what he told us was that if I have a wire in the quantum regime, there are really 2 types of wire: an ordinary garden variety superconductor and what we call a topological superconductor. And at the boundary between these 2 types of wire, there's an object we call a Majorana fermion, but you can think of it as being like half of an electron. And if we allow an electron to be absorbed by the topological superconductor, it sort of dissolves away and disappears, and thereby changes the state of these Majorana fermions. So in this way, there are really 2 different states, one with the extra electron added and one without, and locally these states look the same. This is a topological encoding of information, the type that we can hide from the environment, that we might want to use in a quantum computer. Well, originally Kitaev's idea was a rather mathematical proposal. He had a model in which this phenomenon would occur. And what Raphael and Alicea and others explain is how we can really make this practical by combining a semiconductor wire with a superconductor and some other clever tricks. And just in the past year or so, we've seen the first experimental evidence that an electron really can be absorbed by a topological superconductor and disappear, as I've described, but the experiments are still not definitive, and more experiments will be needed. If that is achieved, it'll be a real milestone for physics, apart from any long-term potential technological implications. Now, can we really use these Majorana fermions for computing? Well, here too, Alicea and Raphael and others had an interesting idea, which is we can imagine a network of wires in which there are T-junctions. And if I want to exchange the positions of 2 of these Majorana fermions, I can do it in 3 steps. First, by using electric fields, move the Majorana fermion around the corner of the T-junction and park it, then move the Majorana fermion that was initially on the right over to the left, and then unpark the first guy. And by that way, we have exchanged the positions of the 2 particles without them ever coming close to one another. That's just what we need to do to perform an operation on topologically encoded data. So that hasn't been done in experiments yet, but we're hopeful that it can be in the next few years. Now, the next hero I want to talk about is Jeff Kimball, another member of the Caltech faculty. Now, Jeff is from Texas, and since I'm a theorist, I've never actually measured him, but I believe he's about 2 meters tall. And his stature has inspired the poets, who have been heard to say, "Professor H.J. Kimball is much larger than a thimble and a veritable symbol of the physicist today. Could it be prodigious height explains his knack for squeezing light, or is Jeff's mind extremely bright? I guess that's hard to say." And the poem goes on, but that's not really the point. The point is that when Jeff joined the Caltech faculty almost 25 years ago, he and I had very little in common intellectually. I was a head-in-the-clouds particle theorist. Jeff was justly famous for his tenacity at taking on great technical challenges and eventually overcoming the obstacles solving problems that other experimental physicists shied away from. But we managed to bridge that big intellectual gulf between us because both of us, in 1994, got very excited about quantum information and quantum computing. And we started what at the time we called the Quantum Computing Club at Caltech, which grew over time. And Jeff and I established, after a few years, the Institute for Quantum Information at Caltech. And we were joined later by Alexei, who by that time was on the Caltech faculty, Leonard, and Gil. The idea of the Institute for Quantum Information is that we could bring together people from a wide variety of backgrounds who approach quantum information from different perspectives, some computer scientists, physicists, information theorists, and create synergy that would make possible discoveries that couldn't have occurred by these people acting alone. And we're proud of the success that the IQI had, making Caltech one of the leading centers for theoretical quantum computing research for a number of years. And many of the young people who passed through as postdocs have gone elsewhere around the world where they are now faculty and are among the leaders of a burgeoning new field. So in the IQI, we address many of the problems I've already been talking about concerning quantum computing. What are quantum computers good for? Can we really build them? How will we build them? How can we get them to be robust with respect to noise? But you know, I'm not an engineer. I'm a theoretical physicist. And what interests me the most is the ways in which ideas about quantum information and quantum computing can have an impact on physics across a very broad front. And one particular way in which our ideas about quantum information have had a very broad impact concerns what we call the monogamy of quantum information. Correlations in classical systems are what we could call polygamous. If Alice and Bob both read the newspaper, they have correlated information. Carrie can come along and read the newspaper as well. And then she is just as correlated with Bob as Alice is with Bob and Alice is with Carrie. Quantum correlations aren't like that. They're not so easy to share. If Alice and Bob are fully entangled with one another, that will mean that Bob has fully used up his ability to entangle on Alice alone. And Alice might want to entangle with Carrie, but he can't. Not without giving up some of his entanglement with Alice. And if he wants to fully entangle with Carrie, he can't entangle with Alice at all. And that's what we call the monogamy of entanglement. As you can imagine, monogamy is extremely frustrating. Naturally, Bob would very much like to entangle with both Alice and Carrie. However, he has to strike some compromise between how quantum correlated he becomes with Alice and how much with Carrie. And this property of quantum correlations has impact in many ways. It's important for cryptography, because if Bob and Alice are fully entangled with one another, they can use their shared quantum correlation to establish a secret key that they can use for private communication. And because they're fully entangled, Carrie can't be correlated with them at all, which means that she can't eavesdrop on their private conversation. It's important in understanding the quantum phases of matter. If there are many atoms in a system with many particles, each atom might want to entangle with other atoms. But when an atom entangles with its neighbor, that limits its ability to entangle with other neighbors. And therefore, there are different patterns of entanglement that can occur that we're trying to understand and classify, and a lot of progress has been made on that in just the last few years. Monogamy is important even in the context of black hole physics. Black holes evaporate. They emit radiation, and the radiation coming out of a black hole wants to be entangled both with systems outside the black hole and systems that are inside. And it's not possible to have it both ways. And we're still struggling to understand how the radiation coming out of a black hole resolves that conflict. Now, in just the last couple of years, again, thanks to leadership from Jeff, the IQI has become part of a broader center the Institute for Quantum Information and Matter, supported by the National Science Foundation and the Gordon and Betty Moore Foundation. And in the IQIM, we have a very diverse portfolio of experimental activities, aside from the theoretical activity that began in the IQI. And although these experimental explorations are quite diverse, there's a common theme that connects them. In the IQIM, we are exploring a new frontier in physics. It's not the frontier of very short distances, as in particle physics, or very long distances, as in cosmology. It's a frontier of complexity, what we call the entanglement frontier. We are trying to scale up quantum systems to larger and larger size, obtaining systems that are more and more entangled, knowing that as we do so, it will be more and more difficult to predict, based on our established methods or our digital simulations, how those systems will behave. So we can expect surprising and delightful behavior, which we're eager to explore. Well, there are some other things I'd like to tell you about the IQIM. One is that we have a logo, which was designed with the help of a talented designer, Margaret Sanchez. And what we did with Margaret is we wanted a logo that would evoke the idea that when you make a measurement in the quantum world, the observer is an active participant. The observer decides, for example, whether to open door number 1 or door number 2. So each one of the characters in the logo is only half there. And you, as the observer, complete the letter, complete the observation. We have a website, iqim.caltech.edu, where you can find out more about what we're doing. We have a blog, quantumfrontiers.com, where IQIM researchers reflect on our science from the perspective of their personal experience. Sometimes we tweet, usually about entanglement. We have birthday parties. We have hats emblazoned with the IQIM logo. And with the help of Alicia Hardesty, the fashion designer who starred on Project Runway, we have designed the IQIM t-shirt, available in both men's and women's styles. Now, skeptics might say, why do you need hats? Do you really need t-shirts? Well, yes, we do. Because it's true that we go about our quiet lives, usually, assuming our secret identities as mild-mannered scientists. But we are at all times mindful of the location of the nearest phone booth, knowing that when the situation calls for it, we can, in a moment's notice, expose our superpowers, the power of quantum information. Now, those of us who do quantum information theory mostly occupy Caltech's beautiful Annenberg Center for Information Science and Technology, where you'll often find us in the atrium talking about balls, boxes, beavers, the whole thing. But IQIM is really a much broader community than that, involving, as Tom said, much of the Caltech physics department, as well as computer science and applied physics. And there's a community of young people who are very excited about the mission of the IQIM and are interacting strongly with one another, so we're having a lot of fun. But if I want you to understand the IQIM community, perhaps the best way to explain it is through the eyes of a talented artist, Hiram Parveen Bilal, who worked with us to produce this video about IQIM. Well, I hope the video speaks for itself, but if you would like further insight into the thinking behind it, you might want to look at Aram's post on our blog. That's right, I did say a high-fashion shoot for geeks. The IQIM tagline, "Nature is subtle," is inspired by a famous pronouncement by Einstein. "Subtle as the Lord, but malicious he is not." For all his genius, Einstein underestimated the subtlety of nature when he derisively dismissed quantum entanglement as spooky action at a distance. And our mission at the IQIM is to relish, to explore, and exploit the glorious subtlety of the quantum world in all its facets and ramifications, and, when the occasion calls for it, to unleash the superpower of quantum information. So I would like to continue with rolling the credits for the video, so we can all acknowledge those who contributed to creating it, and say, thank you all for coming tonight and for listening to me. It's been a lot of fun. Thank you.